So, today we'll learn about mathematical logic. So, the first and the most important part in mathematical logic is basically the logical connectives that are used to connect the sentences or join the sentences. So, there are five such logical connectives, namely and, or, if then, if and only if, and not. So these basically five logical connectives we'll use in this chapter. So and connective is also known as conjunction, or connective is also known as disjunction, if then is known as implication. For example, if a particular situation occurs, then this will occur. So that's basically implication or condition. The fourth connective being if and only if, that is it is also known as the biconditional or IFF. It's written as IFF. And the fifth and the last connective being the negation or the not. That means the negation of particular sentence. So now we will learn what are the symbols of this, like how do we represent or how do we denote them, how do we denote the connectives. And is denoted by this symbol, or is denoted by this symbol, if then is denoted by this symbol, or this also can be used to denote a condition or an implication. And in the fourth connective, that is if and only if, that is a biconditional, it is denoted by an arrow with the arrow pointing on both the sides. So this is basically biconditional or double implication. The last being negation. Negation is denoted by this sign. So now we'll take a small examples of these connectives. Suppose we have two sentences or two sentences P and Q. So the end of P and Q would be denoted by P and Q, or would be denoted by P or Q. If P then Q would be denoted by P arrow Q. So if P then Q. Now P if Q, this is if has double F, okay, so it would be denoted by P double arrow Q. And negation would be simply, if there's a sentence P, so the negation of P would be simply this and P. So this negation of P is known as negation. Okay, so after this we'll be seeing the truth tables of each and every logical connective. So now taking first or. Okay, so in or we have considered all the permutations and combinations of a T of the true and false, and we have written it. P can be true true false false, Q can be true false true false. Okay, so now first is true true, P and Q both are true, then P or Q would be true. True false or would be true, false true it would be true, false and false it will be false. So in or we have to note that if any of the statement is true, then the result would be positive, and if both the statements are false, then the result is negative. Coming to and, it's just the opposite. True and true will always give us true, true and false will give us false, false true will give us false, false false will give us false. That means that even if one statement in and is false, the result becomes false. So for in and, for the statement to be positive or to be true, both the statements must be true for and. Now we'll see the implication, that is P implies Q. True true would become true, true and false. If the first statement is true and the second statement is false, then the result would be false. False true true, false false true. Now we'll see the biconditional, that is double implication. So true true will become true, true false will become false, false true would become false, false false will become true. And for negation we'll take P and negation of P, true and false. So P, so the negation of true would be false and the negation of false would be true. So the truth table for all the connectives is learned. Now, what are the types of statements that we use in this chapter? A statement that is always true is called as tautology. A statement which is always false is known as contradiction. And a statement which is neither of the two, that means it's not, we can't tell whether if it's true or whether if it's false, so it's also known as contingency. So now coming to the converse, the contrapositive and inverse of particular statement. So if P arrow Q is a conditional statement, we have been given that P arrow Q is a conditional statement, then what would be the converse, contrapositive and inverse of that particular statement? So the converse of this statement would be Q implies P, just the opposite of it. If in question is P tends to Q, or P implies Q, then it would be Q tends to P. The contrapositive of the statement would be just the negation of the converse, that is, negation of Q implies negation of P. So converse and contrapositive is done. Coming to inverse. So what is inverse? Inverse is just the negation of the conditional statement that is given to us. So if the conditional statement given to us is P implies Q, then the inverse of it would be negation of P implies negation of Q. So converse, contrapositive and inverse of a statement is learned. Now coming to duality. So what is duality? Two compound sentences are said to be dual of each other if one can be obtained from other by replacing this with this and vice versa. So if you replace the and with or and or with and, it would be duality, and the connectives and or are duals of each other. So we have to remember that and or are and or are always dual of each other. Now coming back to negation of a statement, so we'll apply negation to each and every logical connective that we have learned so far. So negation of P or Q is equal to negation of P and negation of Q. So whenever we open the brackets, negation is just out of it. So whenever we open the brackets, we change the sign, that is negation of P or becomes and negation of Q. Similarly, negation of P and Q would become negation of P or negation of Q. It's very simple. Now, negation of P implies Q would be P and negation of Q. Negation of P double implication Q would be P and negation of Q or Q and negation of minus P. So negation of each and every connective is learnt now. So mathematical logic has a very important application in circuits that we are going to learn now. So suppose we have considered a circuit here. So this is basically a circuit. The battery, the lamp and the two switches are given to us. Okay, so these both switches are given to us and we have to see whether the lamp is burning or not. So in AND condition, let P, that means switch S1 is on, and Q, that means switch S2 is on. So in AND condition we had learned that for the statement, for the result to be true, both the statements must be true in AND. So for the bulb to light, for the bulb to glow, we know that the both of the switches must be on, then only will the bulb glow. Otherwise, if only one switch is on or one switch is off, the bulb won't glow. So coming to OR. So in the same switch, now we'll let P, that is switch S1 is on, Q, that is switch S2 is on. So in OR we had learned that even if one of the condition is true, that means the result is positive. So if one of the bulb is glowing, then the one of the switch is on, that the bulb will glow. So either of them should be on for the bulb to glow. So OR is also learned. Now what about negation? If two or more switch open or close simultaneously, then the switches are denoted by the same letter. Suppose P. If P denotes switch S closed, that means P means that switch S is closed. So the negation of P means that switch S is open. So now we'll see the various properties or the various shortcuts that we would be using in this chapter. So first property is the commutative property. Now what do you mean by a commutative property? That means that if P or Q is equivalent to Q or P, that is the order doesn't matter. P or Q is nothing but Q or P. And similarly P and Q is equivalent to Q and P. So the next property now is the associative property. In this, bracket P or Q or R is equivalent to P or Q bracket Q or R. So this property tells us that the place of the location of the bracket doesn't matter. Even if the bracket is here, so it doesn't make any difference. So if the bracket is changed from here to here, it would give us the same result. Similarly, bracket P and Q and R is equivalent to P and bracket Q and R. So this is nothing but the associative property. Associative property is basically the relocation of brackets that doesn't change the result. The third property is the distributive property. In this, P or Q bracket Q and R is equivalent to, so now we'll open the brackets in the distributive property, that is P or Q and the middle sign is AND, so here the middle sign is and P or R. Similarly, P and Q or R, so the middle sign is OR, so middle will come here, P and Q and P and R. So this is basically the distributive property that distributes P. Now De Morgan's law. De Morgan's law is nothing we had studied earlier. So De Morgan's law states that negation of P or Q is equivalent to negation, we'll open the brackets here, negation of P or now becomes and negation of Q. Similarly, negation of P and Q is equivalent to, we'll open the brackets, negation of P or negation of Q. So this is basically the De Morgan's law. Now what about the absorption law? Absorption law, P or bracket P and Q is equivalent to P itself. Similarly, P or P bracket P or Q is nothing but P itself. So this is nothing but the absorption law. Coming to the identity law states that T here represents tautology and F represents contradiction. So T basically is a true statement and F basically is a false statement, and P could be any statement, it can be true or it can be false. So P or true will always be true, because in OR we have learned that irrespective of the second option, if the first is true, so the result would be true. So this is clear. The second point, P or false is equivalent to P. That means we can't, so if one is false, so we can't say, if the second is false, so it can be true, if the second can be true, so it can be false. So we can't really say about P, so it will be equal to P. Second would be P and T is equivalent to P, and the fourth would be P and F would be equivalent to P. So the eighth law is P and F would be equal to false. So in identity laws, P and a true statement would always be equivalent to P itself, because we can't say whether it would be true or false. Now P and false would always be false, because in AND we know that even if one of the statement is false, the result would be false. Now we'll come to the complement laws. So what does the complement laws say? P or negation of P is always true. So suppose if we take P as true and or negation of P would be false. So true or false will always give us true. Okay. Next, P and negation of P would always give us false. That means if we assume P to be true, so true and false would always give us false. Similarly, negation of negation P would give us P. Fourthly, negation of true is equivalent to false, and similarly negation of false is equivalent to true. So this completes our complement laws. Coming forward to idempotent laws. So what does the idempotent laws say? It says that P or P is nothing but P itself. So a statement's or would be the statement itself, and a statement's and would be the statement itself.